Let's learn about laws of exponents. In this lesson, students will learn to rewrite products into exponential notation. Students will simplify expressions using laws of exponents. Students will rewrite radicals into rational exponents and vice versa. Students will simplify radicals and expressions with rational exponents, and students will rationalize denominators. So some of the things in this lesson will be review, but some things might be new. Right? So if it's review for you, great. And if it's new, right, well, then you're going to learn some important things about exponents. So first of all, let's just start at the beginning. Exponential notation. So if we have, and this, by the way, is in your notes, so you don't have to write it down. If we have any number raised to any real number at all raised to a positive power, the number that we're raising to a power is called the base. When we raise a base to a power, we're essentially multiplying that base by itself a number of times that's equal to the exponent. So for instance, if I have 1/2 to the 5th power, that means I'm multiplying 1/2 by itself 5 times. Right? And I can simply multiply the numerator. If I multiply 1, no matter how many times, it's still going to be 1. And 2 times 2 times 2 times 2 times 2 would be 32. So you can either think of it as multiplying 1/2 by itself 5 times, or you can just raise 1 to the 5th power, which is the same as multiplying 1 by itself 5 times, and 2 to the 5th power, which is the same as multiplying 2 by itself 5 times. Let's look at the second and third examples. Notice they look very similar, but they're not the same. In the first example, we have parentheses. So if we have parentheses, it means everything in the parentheses is going to be raised to that power. So -3 to the 4th power is -3 times -3 times -3 times -3. All right, so I've got an even number of negatives, so that's going to be positive. And and 3 times 3 times 3 times 3, that's going to be a positive 81. By the way, there's no difference between using parentheses to show multiplication and a dot. I just happened to use a dot when it came to the fraction in the first example, and I used parentheses in the second example. But they both are illustrating multiplication. Now with -3 to the 4th power, without the parentheses, we had to use order of operations. Raising to an exponent is first. That negative sign is the same as multiplying by -1. So -3 to the 4th power without the parentheses is the same as -1 times 3 to the 4th power. We would raise to a power before we would multiply. So this would be the same as, actually let me use a different color so these stand out as being different colors. Come on. And, oops, where'd color go? Well, it's not going to give me color as a choice. I'll just rewrite it. Okay, so it's the same as -1 times 3 to the 4th power. So we're going to raise to the power first. That's going to be -1 times 3 times 3 times 3 times 3. 3 times itself 4 times, that's going to be 81. And then we're going to multiply by the -1. So notice that if the negative is not in the parentheses, then your answer is going to be negative. No matter how many times you multiply the value by itself. All right, so if A is not 0, because you actually cannot raise 0 to the 0 power, that's actually undefined, and you cannot have 0 in a denominator, we have two properties here for 0 and negative exponents. So for 0 as an exponent, anything raised to the 0 power is 1. Now you just have to take me at my word for that for one slide, and then I'll demonstrate why on the next slide after we look at some rules for exponents. The second rule says that anytime you raise a integer to a negative power, it's the same as raising the reciprocal to that power. Now I can write that as 1 over a to the nth, or I can write that as 1 over a to the nth. This would be the same thing, because raising 1 to any power is still going to be 1. By the way, this is in your notes, and if you want, you can add that little part to it. All right, so let's do a few examples using the properties of 0 and negative exponents. So all 4/7 is being raised to the 0 power. All right, so that means that is going to be a 1, because we're raising a number that's not 0 to the 0 power, and our answer will be 1. If we raise x to the negative 1 power, it's the same as raising 1 over x to the positive 1 power. And I could write it like that, or I could write it like this. This will be the exact same thing. But either way, it's going to be 1 over x, because anything to the first power is just itself. And now we have negative 2 to the negative 3 power. That's the same as raising negative 1/2 to the third power. And I really prefer putting this in parentheses, because quite honestly, if I write that 3 next to the 2, I have a feeling it's going to look like negative 1 over 23. Now it's very clear that we're raising 2 to the third power. So negative 1/2 to the third power is the same as negative 1/2 times negative 1/2 times negative 1/2. The negative is being raised to the power, right, because we have parentheses. So that's going to be a negative. We have an odd number of negatives there. So it's going to be negative 1/8. It's 2 times 2 times 2 is 8. All right, so a little work there with 0 as an exponent and negative exponents. And I really hope that is a review for you, as well as exponential notation. All right, so let's take a look at laws of exponents. And you do have this in your notes. That you have the information under the white box, so you don't have to write this down. But I want to do it with you, not just go over the answer so it makes sense. But you don't need to write anything down because you do have it in your notes. All right, so our first law is what to do if we multiply like bases raised to a power. If we multiply like bases raised to a power, we simply add the exponents, and I'll show you why as well. So 3 squared times 3 to the 5th power is the same as 3 to the 2 plus 5 power, right, which is the same as 3 to the 7th power. All right. So 3 to the 7th power is going to be 2,187. Now, to see why that's true, we could expand it to make sense of this. So 3 squared is the same as 3 times 3. And 3 to the 5th is the same as 3 times 3 times 3 times 3. So, oops, one more 3. So you can see we've got 7 factors of 3 there. 3 to the 5th power divided by 3 squared. All right, so let's look at our law up above there. If we divide like bases raised to a power, we're going to subtract the exponents. So that means that 3 to the 5th divided by 3 squared is the same as 3 to the 5 minus 2 power, which is the same as 3 cubed, which is 27. To say that that is indeed true, if we were to take 3 to the 5th power, that would be the same as 3 times 3 times 3 times 3 times 3. Divided by 3 squared, that would be 3 times 3 in the denominator. And we could simply cancel out 2 factors of 3 between the numerator and denominator, and that would leave us with 3 factors of 3, right? So you don't need to expand, right? If you're multiplying or dividing, you add the exponents when you multiply, and we can see why. And when you multiply like bases raised to a power, you add the exponents, and we can see why. When you divide like bases raised to a power, you subtract the exponents. By the way, it does have to be the same base. Okay. Now, I said I'd explain why anything to the 0 power is 1. And you probably just took it for granted, and no one ever really showed you why. All right, so I'm going to use powers of 3 since we've been working with powers of 3 here. And I'll start with 3 cubed. All right, so 3 cubed, we can agree, is the same as 3 to the 4th divided by 3. 3 to the 4th is 81 divided by 3. That's going to be 27. 3 squared is the same as 3 cubed divided by 3, right? Because 3 minus 1, right, that would be 2. So that would be 3 cubed is 27. Divided by 3, that's 9. 3 to the 1st power, that's the same as 3 squared divided by 3, right? Because 2 minus 1. Anything, if you have one factor, right, it's raised to the 1st power. 2 minus 1 would just be 1, so that would be 3. 3 to the 0 power, that would be the same as 3 to the 1st divided by 3. 3 to the 1st is just 3. 3 divided by 3 is 1. All right, so that's the way you can think of it. When we do that repeated division to get to the next factor, you can see that if I divide 3 by itself, so 3 to the 1st power divided by 3 is the same as 3 to the 1 minus 1 power, which is 3 to the 0 power, and 3 divided by 3 is 1. Right? So 3 to the 0 power is 1. All right, so there's just a little explanation of why that's true. You do not need to write that down. Right, just explaining why it's true. And I'm going to move this I'm going to either erase it or move it out of the way later before I post this. All right, so now the next one, if we raise something with a power to a power, it's called powers rule, we multiply the exponents. All right, so 3 squared to the 5th power, that would be the same as 3 to the 2 times 5 power, or 3 to the 10th. And I've now exhausted the powers of 3 that I have in my head. So, oops, turn on the calculator there. And that would be, whoops, and I just dropped it. Sorry, 59,043. I know 3 to the 7th power, and that's it. All right, now to think about why would that be true? If I'm raising 3 squared to the 5th power, that's the same as 3 squared times 3 squared times 3 squared times 3 squared times 3 squared. And you can see each of those 3 squareds, remember, that would be 2 factors of 3. Well, I've got 2, 4, 6, 8, I've got 10 factors of 3. Right? If you've got a product raised to power, you do in parentheses, we're going to take care of the parentheses. We can multiply those and take care of in the parentheses first. Or since it's a product, so 3 times 4 squared would be the same as 12 squared. It would also be the same as 3 squared times 4 squared. Only for a product, or if you're going to find out a quotient, don't ever do that to a sum or difference, right? It would not be the same. So, and we can show that this is actually true. 12 squared is 144. No problem there. 3 squared is 9. 4 squared is 16. 10 times 9 is 90. 6 times 9 is 54. 90 plus 54 is 144. So you see you do get the exact same thing, a little informal proof there. That also does work too if you are raising a quotient to an exponent. You do raise the numerator to that power and the denominator to that power. What I would not do is make that 0.75 squared. I can't do that in my head, but I can certainly do 3 squared and 4 squared in my head. 3 squared would give us, so it'd be the same as 3 squared divided by 4 squared. 3 squared is 9 and 4 squared is 16. All right, so if you have a product or a quotient, right? For a product, you can raise each factor to the power. For a quotient, you can raise the numerator and the denominator to a power. Only for products and quotients. If you've got a fraction to a negative exponent, you raise the reciprocal to the positive power. Right? So to raise a fraction to a negative power, invert the fraction, change the sign of the exponent. So 3/4 to the negative 2 power is the reciprocal 4/3 to the positive 2 power. So that's going to be 4 squared, which is 16. Actually, I'll write it in. 4 squared, which is 16, divided by 3 squared, which is 9. All right, and now we have the numerator and denominator both raised to a negative exponent, but it's not the same negative exponent. So to move a number raised to a power from the numerator or denominator to the denominator, or from the denominator to the numerator, we don't want negative exponents. Right? If you have a negative exponent, you can think of it as this. I'm on the wrong side of the fraction bar. Right? So A needs to be not in the numerator, but in the denominator, and change its exponent to positive. B needs to be not in the denominator, but in the numerator, and change its exponent to positive. Right? So that's all it really means. If you have a negative exponent, you are essentially on the wrong side of the fraction bar. Switch to the other side. And you can do that easily so long as what you're dealing with is either a single term or product of terms. So 3 to the negative 2 power, that should go to the denominator and be 3 squared. 4 to the negative 5 power should go to the numerator, and that would be 4 to the 5th power. And 4 to the 5th power would be 256 times 4. Is that 1024? Yeah. And 3 squared is 9. And by the way, if you're wondering, does any of these reduce, these fractions? If the original doesn't reduce, so it's like 3/4 doesn't reduce, neither does 3/4 raised to a power. Right? 4 raised to a power and 3 raised to a power are not going to reduce because 4 and 3 don't reduce at all. So neither will the result. All right, and you should have the exact same things under here. Right? Except I expanded them. Right? You don't have to worry about expanding them. It doesn't matter. Right? It's the rules. These are in your notes. So using laws of exponents, let's do these real quick. So we've got a product of like bases raised to a power. If you're multiplying like bases raised to a power, you simply add the exponents. So x to the 4th times x to the 7th is the same as x to the 4 plus 7 power, which is x to the 11th. Here we've got, so you can do this one of two ways. I'll show you both ways. So, and put both ways in your notes. You can either, you've got like bases raised to a power, add the exponents. Right, so that would be y to the 4th plus negative 7, right? We've got, we're multiplying y to the 4th times y to the negative 7th power. That would give us y to the negative 3 power, but we don't like negative exponents, right? So make it the reciprocal, move it to the denominator. 1 goes in the numerator. And then make the exponent positive. So you can think of it this way as a product. Or if you want to simplify that negative exponent right in the beginning, right? You can simplify the negative exponent first. So here it was just multiply. Here it's going to be simplify first. And so that would be y to the 4th. Y to the negative 7's on the wrong side of the fraction bar. That should be in the denominator. And here, if we're dividing like bases raised to a power, we subtract the exponents. 4 minus 7 is going to be y to the negative 3, which should be 1 over y cubed. It doesn't matter which way you simplify. And by the way, you don't need, I'm showing you all these steps because I want to make sure it's clear on notes. I am fine if you add and subtract in your head and don't show all the steps. As long as you're not making errors, it's fine. If you're making a lot of errors, then maybe we should write it out initially as you're just reviewing. All right, so here we're dividing like bases raised to a power. We subtract exponents. So c to the 9th power divided by c to the 5th power would be c to the 9 minus 5 power, which would be c to the 4th power. Do put the steps in your notes, however, so you have them to refer to. If we're raising something with a power to a power, remember we multiply exponents. So b to the 4th raised to the 5th power is the same as b to the 4 times 5 power, or b to the 20th power. If you've got a product being raised to a power, right, you raise each term in the product to the power. So 3x cubed, all of 3x is cubed, right, because we have parentheses. That's the same as 3 cubed times x cubed. You should really simplify out 3 cubed. Yeah, it's 27 x cubed. Not that it's wrong to leave it as 3 cubed, but what if you write your exponent really big and it starts to look like 33, right? Not so good. All right, and then if you have a quotient raised to a power, you raise each of the terms in the quotient. So this is x halves to the 5th power is the same as x to the 5th power divided by 2 to the 5th power. Right, and if I make my exponent too big, notice it starts to look like 25. So let's simplify that so there's no confusion that that's 2 to the 5th, which is 32. Okay. So, laws of exponents. I'm going to see if I have how many more I've got with just exponents, because I'm going to split this lesson into 2. I think we'll do these 2 problems together, and then we'll definitely stop. So let's do the 4 problems together, and then we're going to stop. All right, so we're simplifying expressions with exponents, right? Take care, so remember, order of operations, don't multiply the 2 and the 3 together before you've dealt with that exponent out there. All right, let's cube everything first, and then we can start multiplying, like bases raised to a power. So 2a cubed b squared times 3ab to the 4th power all cubed. We're going to cube that 3ab to the 4th power, which means we're going to cube the 3, we're going to cube the a, and we're going to cube the b to the 4th power. Hope that looks like a 4. And I've got the right amount of parentheses, okay. All right, so still nothing with this first term here. 3 cubed is 27. And b to the 4th power cubed would be b to the 12th power. All right, so now we can multiply the coefficients together, and we can multiply the like bases together. So this is going to be 2 times 27. The two coefficients can be multiplied. We can multiply the a cubed times a cubed. And we can multiply the b cubed times b to the 12th. Well, 2 times 27, that's just 54. A cubed times a cubed is the same as a to the 3 plus 3 power. B cubed times b to the 12th is the same as b to the 3 plus 12 power. Our final answer is 54, a to the 6, b to the 15th. Now, in terms of U-shelling work, do cube everything first, all right, and show as much work as needed for you to be accurate. All right, I'm okay on these kinds of problems doing that. Let's do the second one. All right, so they're both raised to a power. Let's take care of the exponents first. We've got xy cubed. That means we're going to raise x to the third power, and we're going to raise y to the third power. All right. And then we're going to raise y squared to the fourth power, x to the fourth power, and z. All right. Let's simplify these out. So we've got x cubed. And you know, we're going to write this, I'm going to write this as one fraction later together. So y squared to the fourth power is the same as y to the eighth power. And then we have x to the fourth, and then this is all times 2. All right, so in the numerator there, let's simplify the x's. All right, so that's x to the 3 plus 4 power, because we're multiplying like bases raised to a power, so we add. If you don't mind, let's take care of the y's at the same time. If we have 1 in the numerator and 1 in the denominator, we're essentially dividing like bases raised to a power. And when we divide like bases raised to a power, we subtract exponents. The 2 is in the denominator. So this is going to be x to the 7th power times y, 8 minus 3, that's y to the 5th power, all divided by 2, and we're done. This is not the only way. You could, if you like canceling things out, that's fine. It's the same thing, right? But just showing you those properties, this is one way you can simplify that. But no matter what, your answer should be x to the 7th power, y to the 5th power, divided by 2. Let's do the last two examples. All right, so I feel it is easier to take care of those negative exponents first, right, and make them positive, and then deal with simplifying, right? Because it's just easier to work with positive numbers than it is negative numbers. So we're good with the 6 and the s. Those both have a positive exponent on it. But the t has a and by the way, we've got nothing but terms that are multiplied and divided. If I've got nothing but terms that are multiplied and divided, I am free to simplify negative exponents by simply moving them to the denominator if they're in the numerator, and moving them from the denominator to the numerator as well. All right, so the 6s is fine. That t, though, should go to the denominator and give it a positive exponent. The 2, and I'll put the 2 first, just because we normally do that. The 2 is fine. The s, however, should go up to the numerator because it has a negative exponent, and that's a t. A little fuzzy there. It's fine because it has a positive exponent. So now we can reduce the 6 and the 2. That would be a 3. If we have s times s squared, that's the same as s to the 1 plus 2 power. And we have t to the 4th times t squared. That's the same as t to the 4 plus 2 power. So that's going to give us 3s cubed divided by t to the 6th power. And we're done. And the last one there. All right, so the whole thing is being raised to the negative 2 power. Make it the reciprocal, and you can raise that all to the positive 2 power. They both switch. All right, and now all we got to do is we got to square everything. So we've got 3 squared times z cubed all squared divided by y squared. So 3 squared is 9. That thing is a z, and it looks an awful lot like a 2. So z cubed to the second power is the same as z to the 3 times 2 power, or z to the 6th power, divided by y squared. And nothing we can simplify because we have no like bases. And that's it. All right, so I'll see you in the next video, and we'll learn a little bit more about, we'll learn about rational exponents and radicals. Thanks for watching. Bye for now.